Welcome to our exploration of big data, inspired by Ghislaine Forney's comprehensive textbook. In this video, we'll journey through the evolution of databases, the rise of large-scale data management, and the core principles that shape how we store and process information today. Whether you're a student, educator, or simply curious about how the world's data is organized, this series will provide a clear, logical path from the origins of data storage to the latest in distributed systems. Let's begin by understanding why big data matters and how it impacts our daily lives and scientific progress. To grasp the concept of big data, we need to appreciate scale. Just as astronomy forced us to think in terms of kilometers, gigameters, and even yottameters, the digital world has rapidly moved from bytes to terabytes, petabytes, and beyond. In a few decades, computers have gone from storing tiny amounts of data to managing volumes that rival the vastness of space. This exponential growth challenges us to rethink how we store, access, and make sense of information, drawing fascinating parallels between the universe and our digital landscape. The story of databases begins long before computers. Nature itself stores data in DNA, and early humans relied on memory and oral traditions. The invention of writing on clay tablets marked a major leap, allowing information to persist for millennia. Surprisingly, some ancient tablets even contained relational tables, hinting at our innate tendency to organize data in structured forms. The printing press revolutionized knowledge sharp, and finally, modern computers accelerated data processing, setting the stage for today's database systems. The modern era of databases began in 1970, when Edgar Cudd introduced the concept of data independence. This idea separated the logical view of data from its physical storage, making databases more user-friendly and adaptable. Cudd's relational model, based on tables, became the foundation for most database systems. As data volumes exploded, new models emerged: key-value stores, wide-column stores, document stores, and graph databases, collectively known as NoSQL. These innovations addressed the limitations of traditional systems and enabled the management of massive, diverse datasets. Big data is often defined by three key characteristics: volume, variety, and velocity. Volume refers to the sheer amount of data being generated and stored, which is growing exponentially. Variety highlights the different shapes data can take: tables, trees, cubes, graphs, and vectors, each requiring unique management strategies. Velocity addresses the speed at which data is produced and needs to be processed. These three V's drive the development of new technologies and approaches in data science. Volume of digital data worldwide is staggering, approaching 100 zettabytes as of 2021. This growth is fueled by automated data collection from sensors, logs, and everyday digital activities. Standardized prefixes like kilo, mega, giga, and beyond help us quantify these immense amounts. However, confusion sometimes arises between powers of 10 and powers of 2, leading to terms like cubba and mubba. Understanding these units is essential for anyone working with large-scale data. Data is no longer confined to simple tables. Today, we encounter trees like XML and JSON, cubes for business analytics, graphs for network data, and vectors for unstructured data such as text, images, and audio. Each shape presents unique challenges and opportunities. For example, tree-shaped data enables flexible document storage, while graph databases excel at representing relationships. The rise of AI and machine learning has further increased the importance of vector data and embeddings. Velocity captures how quickly data is generated and must be processed. With modern sensors and digital platforms, data flows in real time, demanding rapid storage and analysis. The evolution of storage devices, from the IBM iMac 350's 5 MB capacity to today's SSDs with hundreds of terabytes, illustrates dramatic improvements in capacity, throughput, and latency. However, while storage and speed have increased, latency improvements lag behind, creating new challenges for data engineers. Overcome the challenges of velocity, modern data platforms use parallelization and batch processing. By dividing tasks among many machines or people, massive datasets can be processed efficiently. For example, if a huge book is split among 1 million readers, it can be finished as quickly as a single person reading a small book. Batch processing further improves efficiency by grouping records and processing them together, rather than one at a time. These techniques are foundational to today's big data technologies. Data isn't just about size, it's about managing and analyzing data that's too large for a single machine, while addressing the growing gaps between storage capacity, throughput, and latency. Big data technologies are designed to handle these challenges, enabling organizations to extract value from vast, complex datasets. This definition sets the stage for understanding the portfolio of tools and systems that make up the big data ecosystem. Data powers groundbreaking applications across science and industry. At CERN, high-energy physics experiments generate 50 petabytes of data annually, requiring sophisticated filtering and storage strategies. The Sloan Digital Sky Survey has created the most detailed 3D map of the universe, collecting hundreds of gigabytes nightly. Even DNA and RNA technologies are now used for data storage and manipulation, blurring the lines between biology and computer science. These examples highlight the real-world impact and diversity of big data applications. Journey from raw data to wisdom involves several stages. Data is collected and stored, transformed into information, then synthesized into knowledge, and finally distilled into wisdom. Big data technologies focus on the first stages: storage, management, and processing, while machine learning and AI build on this foundation to generate insights and predictions. Understanding this pyramid helps clarify the scope and goals of data science as a discipline. Master big data, students should be able to recount the history of databases, explain key concepts like data independence, and distinguish between data information and knowledge. Familiarity with the main data shapes, standard prefixes, and the three VARs is essential. Understanding the differences between NoSQL technologies and being able to cite real-world examples of massive data use rounds out a solid foundation for further study. Cornerstone of modern data management is data independence. This principle separates the logical view of data, how users see and interact with it, from its physical storage. Thanks to data independence, users can query data without worrying about where or how it's stored, and systems can evolve without breaking existing applications. This concept, introduced by Edgar Codd, remains vital even as databases scale from single machines to massive clusters. Typical database management system is built on 4 layers: the logical query language, the logical data model, the physical compute layer, and the physical storage layer. While the logical layers define how users interact with data, the physical layers handle the actual computation and storage. Over the past 2 decades, the physical layer has shifted from single machines to distributed clusters, but the logical experience for users remains consistent. Despite the rise of new data models, the lessons from 50 years of relational database management remain relevant. The relational models focus on tables, logical abstraction, and standardized query languages has influenced even non-relational systems. Data independence applies to all data shapes, tables, trees, cubes, graphs, and unstructured data, ensuring that users can work with data logically, regardless of its underlying structure. Understanding databases requires some basic mathematics, especially the concept of sets and relations. Sets are collections of unique elements, and relations are subsets of Cartesian products of sets. These ideas underpin how tables and records are structured in databases. For example, a table can be seen as a set of tuples, each representing a record with specific attributes. This mathematical foundation ensures consistency and clarity in data modeling. Databases use several standard sets, such as natural numbers, integers, decimals, and strings. The set of all possible values V includes everything that can be stored digitally: numbers, dates, text, and even complex structures like lists and trees. Atomic values are those that aren't structured further, like individual numbers or strings. Recognizing these sets helps in designing robust and flexible data models. The heart of relational databases are tables, attributes, rows, and primary keys. Tables organize data into collections of records, each with defined properties. Attributes or columns describe the properties, while rows or records hold the actual data. The primary key uniquely identifies each record, ensuring data integrity. These concepts are the building blocks of relational data management. Formally, a table is a relation over the domains of its attributes, a subset of the Cartesian product of those domains. Each record is a tuple of values, one for each attribute. While the mathematical model uses ordered tuples, the logical relational model indexes values by attribute names, not positions. This abstraction allows for flexibility and clarity in how data is stored and accessed. In practice, each record in a database can be viewed as a partial function mapping attribute names to values. For example, a record for Albert Unston might map name to Unston, first name to Albert, physicist to true, and year to 1905. This approach highlights the logical structure of data and supports flexible, extensible data models that can adapt as requirements evolve.